So MIPS here, okay, it's used as a performance metric. Okay, so we use it as a performance metric and means millions of instructions per second. That's MIPS. Okay, so it's an instruction rate. So people thought about it as a performance metric that we can actually count how many millions of instructions you can complete per second. So look at the program and how many millions of instructions you can complete per second. Okay. So if you have a faster machine, you can, if you have a faster CPU, you can actually execute, we can have a larger MIPS. Very simple, right? So if you have a faster CPU, this would result in a larger MIPS, and that's an indication of performance. Okay, so the higher the MIPS rate, the better. Now, if you would like to quantify it, quantify means you would like to have a number. Okay, so you would like to have a number. Okay, that would represent the MIPS rate. How do you get this MIPS rate? You divide the instruction count. Okay, so in order to calculate MIPS, what you have to do is that you have to count the total number of instructions, the instruction count, divided by the execution time. But this will give you instructions per second. So count the instructions in the program and look at the execution time in seconds and divide. But this will give you instructions per second, but I need actually millions of instructions per second. So convert it to MIPS by dividing by 1 million. So that's here the 10 to the power 6. That's the million. Okay, if you don't really have here the million, it will give you instructions per second. That's it, very simple. Okay. Now, if you remember the execution time, remember the performance equation. What's execution time? What is the execution time?
Instruction count times CPI times execution time. Right?
Multiplied by what?
Instruction counts multiplied by CPI multiplied by the execution cycle time.
Cycle time. Yeah, it's not execution. Okay, we are calculating the execution time. So let me write it down here again with my pen tool, if I can. Okay, so I'm going to write here that this execution time, always remember the performance equation, so important. So I'm going to write here I here means the instruction count. So let me write it down here. So that's I multiplied by the average CPI multiplied by the cycle. It means, okay, you agree? But this I is the instruction count. So this I, this is instruction count divided by I. They will cancel each other. The CPI appears here. Now 1 over the clock cycle is nothing but the clock rate. You agree?
Yep. Yes.
So that's another. So this is basically another equation for the MIPS rate. Okay. Now, in other words, if I can increase my clock rate, which is the clock frequency, or reduce the CPI, I can improve the MIPS rate. Hello? Nice. Now remember that the execution time. Now you see that we can manipulate these equations, no problem. So if I would like, if I know the MIPS rate, if this is given to me, I can actually calculate the execution time based on the MIPS rate. And I can take this up. So this is the execution time. And then I bring here, so the instruction count is still the instruction count. And then I divide by the MIPS rate. So this is another equation for the execution time based on the instruction count and the MIPS rate. So if I know the MIPS rate for a given program, okay, notice that the MIPS includes the CPI. Notice the CPI appears in the equation. Because the CPI changes from one program to another, it's not fixed. The CPI is not. So the MIPS rate is going to change from one program to another. So you have to count the instructions. So you have to count the instructions. This is the instruction count. Knowing the MIPS rate, you can calculate the execution. Okay. And this is the performance equation. Okay. Instruction count multiplied by the average CPI multiplied by the clock cycles means divided by the clock rate. Okay, so all of these are equations that you can use, okay, to to solve problems, okay, which are related to performance. Now there are some drawbacks here of the MIPS rate. There are 3 problems. Okay, so this is why it's not really a people have criticized, okay, the MIPS rate, although it's an indicator, but there are problems, okay, with the MIPS rate. It does not take into account the capability of instructions. So really, so when I say here capability of instructions, okay, different instruction set architectures have different instructions. So when you would like to compare 2 different computers that have different instruction sets, then this is not really a fair comparison. Yani, for example, I cannot really compare a computer that has an Intel architecture and one which has an ARM processor or a MIPS processor, because the instructions are different. Okay, so if you say millions of instructions per second, what are these instructions? Okay, so that actually is one of the problems. So instructions does not tell you what are these instructions that you are executing in the program. So it does not take into account the capability of instructions. It's vague because the instructions can vary from one architecture to another, from one CPU to another. They are not the same. Maybe you can use them on CPUs, okay, that implement the same instructions of architecture. Yani, for example, you can compare it with one Intel CPU with another Intel CPU. It's exactly the same instructions. Then that would be a fair comparison. But really, if you have, let us say, Intel and ARM and the instructions are different, so, okay, how can you compare them? Okay. So when you have different instruction sets, really, you will be cheating here by looking at the MIPS rate, because when you say millions of instructions per second, what are these instructions? Okay, so that's actually is one of the problems of using the MIPS rate as a metric for performance. A second problem is that it varies between programs on the same computer. Okay, it varies. Yani, even if you use the same, okay, so so MIPS varies here, okay, between programs, even on the same CPU, on the same computer. So even if you are using the same computer, the same instruction set, there is no fixed MIPS rating for a given CPU. So the CPU can give you different MIPS ratings if you run different programs. Why? Why do we get different MIPS ratings? So there is no single MIPS rating for all programs. Even on the same CPU, if you don't change the CPU, you will get different MIPS ratings. Can you tell me why? Can you tell me why?
Because of the CPI is different for each
class? Yes. We have seen in the previous slide that the MIPS here depends on the clock rate and the average CPI. And there is no fixed CPI for all programs. Okay, so the CPI is going to change from one program to another. And for this reason, the MIPS rating is also going to change. Okay, so there is no fixed CPI and there is no fixed MIPS rating for all programs. So it will vary. Okay. The third thing is that now this is here is a problem. The third point is a problem is that MIPS sometimes can vary inversely with performance. It can vary inversely with performance. What does this mean? Yani sometimes the MIPS rating might trick you that if you get a higher MIPS rating, but it does not really mean that the performance is better. Now, what is the true meaning of performance? What is the true meaning of performance?
Time efficiency.
It's just about time, the CPU execution time. So remember that performance means time. So the less the execution time, remember the performance equation, the CPU execution time?
Yes.
This is a true measure of performance. Why? Because it tells you if you can execute the program in less time, then the performance will be better. That's it. So a true measure of performance is the CPU execution time. But sometimes you might get a higher MIPS rating, but the execution time is worse. So therefore, the MIPS rating is not telling you anything. It is actually just sometimes misleading you. Okay, so this is why that actually can be problematic in the case of the MIPS rating. I have an example about this. Here's an example about MIPS. So suppose that we would like to compare, let us say, two different compilers. People actually do this. Okay, so when there are, let us say, different compilers from different companies, for example, if you are using, let us say, the language C++, C or C++, these actually are very well known to produce a very efficient code that will run directly on the machine, much faster code than Java, by the way. So if you are using, let us say, or C++ compilers, you would like really to compare, okay, let us say a compiler from the Intel and a compiler, let us say, from Microsoft, maybe also a compiler which is the GNU C compiler, okay, the GCC, which is open source. So you would like really to compare them and see that actually which compiler can give you faster code. Okay, so compiler technology is also very important for architects. Okay, so here we would like to test two different compilers on the same program, and we have a machine here that is using a clock frequency. Okay, now suppose that for simplicity we only have three different classes. Okay, so we have here three different classes of instructions. Very simple question. Okay, class A, class B, class C. We don't really care. Maybe A is for ALU, maybe B for branches, and maybe C for, let us say, for store. Okay, so suppose that class A would require one cycle per instruction. Okay, one cycle per instruction. For class B, it requires two cycles per instruction, and we have class C will be, let us say, 3 cycles per instruction. Okay. So this is very simple example. And suppose that the first compiler produces, after translating the program and running it, you count the total number of instructions that were executed at runtime. You notice that the program that was generated by the first compiler, because the compiler does the translation, it's a translator. Okay, that's what the compiler does. It is a translator from high level into assembly and eventually machine language. So once you have the program as the executable file, you can execute it. And then once you execute it, you can count the exact number of instructions, okay, that were running, okay, at runtime. You count them. You notice that the first compiler has generated 5 billion class A instructions, 1 billion class B, and 1 billion class C. Okay. You repeat, you use the second compiler, and you translate exactly the same program, which is written in a high-level programming language like C or C++, as I said. And then you run the program again, and you find that it's going to produce 10 billion class A instructions, 1 billion class B, and 1 billion class C. Okay. So clearly here that the first compiler is better because it is the count of instructions is less, but it does not even have to be like this. This is just one example. Okay, so it looks like the first compiler is doing better than the second one because it is generating less 5 billion versus 10 billion class A instructions. Okay, now the question is which compiler produces a higher MIPS rating and which compiler produces a better execution time? So these are the two questions. So how do I calculate the MIPS rating, okay, for these two compilers? What shall I do? And how do I calculate the execution time? Notice that it says for 4 gigahertz machine, the count of instructions is given, the clock cycle or the clock frequency is given, right? So what is needed? Yes.
Calculate CPI.
So what we need to do is that we can calculate the average CPI. Yes. How do I calculate the average CPI?
Frequency multiply.
No, CPI, just CPI. Cycles per instruction. Okay, so we know that actually class A, class B, class C would require 1, 2, and 3 cycles. This is given, right? So let us do it. Okay, let us do it in the next. This is actually the solution. So let us start actually by calculating the CPU cycles. Okay, so how do we calculate the CPU cycles for the programs that were generated by both compilers? So here we have translated the same high-level program, okay, by two different compilers. So in the case of the first compiler, it says that 5 billion class A, 1 billion class B, 1 billion class C. So calculate
Instruction count times the number of cycles.
Okay, tell me now the numbers. Let us put it actually as numbers. So 5 billion should be multiplied by how many cycles?
5 times 1.
Yes.
1 times 2 and 1 times 3. And
that's exactly what I need. Okay. So 5 times 1, because 1 cycle for class A, 1 billion times 2, and 1 billion times 3 cycles. Of course, I'm multiplying here by billion. That's 10 to the power 9. That's actually billion. Okay. So you get in total, you get actually here 5 plus 2 plus 3, you get 10 billion. That's the total number of cycles. You have to write cycles here. Okay. So that's the CPU cycles. Let us repeat for compiler 2. Okay, so compiler 2 is shown here, 10 billion class A, 1 billion class B, and 1 billion class C. So we multiply 10 by 1, 1 by 2, and 1 by 3. That's it. So we get 15 billion. Okay, very simple. That's actually for compiler 2 billion. So that's step number 1, calculate the CPU cycles. Next, let us find the execution time, because it asks you about the execution time. So how do you calculate the execution time?
We divide the CPU cycles by the clock rate.
Yes, yes. You can actually just divide by 4 gigahertz, because gigahertz means billions of cycles per second. So here we have cycles. So divide here the cycles by the clock frequency. So if you divide by 4 gigahertz, you get 2.5 seconds. And then if you divide 15 billion cycles by 4 gigahertz, you get 3.75 seconds for compiler 2. Okay, so remember that this is the program that was translated by the compiler 2. Okay, so it took 3.75 seconds to execute, whereas the program that was translated by compiler 1 took 2.5 seconds to execute. So now the question is, which is doing better, compiler 1 or compiler 2? It's the same program in a high-level programming language. It's the compiler, okay, which is translating it differently. Okay, both programs which are translated by compiler 1 and compiler 2 are going to produce exactly the same results, are going to compute exactly the same thing, but which one is running faster?
Compiler 1.
Exactly. So compiler 1 is actually generating a program that will run faster than compiler 2. Okay, so 2.5 seconds versus 3.75, clearly 2.5 seconds. Compiler 1 is a winner here, is generating faster code. Okay, so that's actually here, the winner is compiler 1. So clearly here that compiler 1 generates a faster program. Notice that we did not change the high-level program. We did not touch it. We just translated by 2 different compilers. Okay, so this is the importance of the compiler. Okay, so whether it generates actually fast code or slow code without touching your high-level program. Okay, it's the same program which is written in a high-level programming language. Right. Now, the second question is, what is the average? Okay, let us calculate here the MIPS rate. Let us calculate the MIPS rate. So the MIPS rate is the instruction count divided by the execution time divided by 1 million, because we would like to get it in MIPS as millions of instructions per second. So what is the instruction count for the compiler 1?
7 million.
Yes, it's 5 plus 1 plus 1. This will give you 7 million. What's the execution time?
2.5 seconds.
Exactly, just put the numbers. So we have 7 billion instructions are executed in 2.5 seconds. So if you divide by 1 million, you get 2,800 MIPS. So that's the MIPS rate for the program which is generated by compiler 1. Now, if I would like to calculate the MIPS rate, which is by compiler 2, I have 12 billion instructions, right? So 10 plus 1 plus 1, these are 12 billion. And these are executed in 3.75 seconds. Of course, I have to divide by 1 million here to convert it to millions of instructions per second. So this will give me a MIPS rate, which is 3,200 MIPS, or in other words, 3.2 billions of instructions per second. So this is 3,200 million instructions per second. You can also convert it to billions of instructions per second if you want to. Okay, so this will give you 3.2 billions of instructions per second for the program which is generated by compiler 2. Now, which one is a higher MIPS rating, 2,800 or 3,200? Clearly, which one is higher?
The second
compiler
one.
1 or compiler? Yeah, so compiler 2 here. Yeah, so compiler 2 is generating a program that runs at a higher MIPS rating. Okay, and the reason why is because it is actually generating 10 billion class A instructions that will take only one cycle each. So really the CPI, the CPI which is generated by the program of compiler 2 is less than the CPI of the one which is by compiler 1. So this is interesting because even though the compiler 2 is generating a program that runs at a higher MIPS rating, 3,200 versus 2,800, still the execution time is worse, okay, for compiler 2. So again, so this can be misleading, okay? So notice that the execution time of compiler 2 is worse than the compiler 1, but its MIPS rating is higher. So the MIPS rating being higher means nothing here. What's important to us is the execution time. That is the bottom line, is the execution time. Okay? Any question about this? So this is the meaning of the MIPS rating. So for this reason,
sorry,
people don't.
I have something not clear for me.
Yeah.
What if we have a higher MIPS rating? What will happen?
It means nothing, because the bottom line is the execution time. So the execution time of the program, which was generated by compiler 2, is worse. It's longer than the execution time of the one which is. So therefore, the compiler 1 is going to win, even though the compiler 2 is generating a program that has a higher MIPS rating. So the MIPS rating here means nothing. And even though actually the compiler 2 has a higher MIPS rating, it does not really mean that the execution time is better. So you always have to go back to the execution time. That's the most important thing about performance, is the execution time. So we say that compiler 1 will produce code which is faster, okay, than compiler 2, because it will take less time. That's it, okay? Regardless of the MIPS rating. Okay?
Okay.
So that actually is the last point that I wanted to talk about, that when I talk about one of the drawbacks, okay, of the MIPS rating is that sometimes you get a higher MIPS rating even though the execution time is worse. Okay, so in that case, we don't look at the MIPS rating and we just go to by the execution. Right. Another important concept which is related to performance is Amdahl's law. Okay, so what is Amdahl's law? It is a measure of speed up. So what we are trying to do is that we are trying to measure speed up. That's the Amdahl's law. So this is how a program performs after improving a portion of a computer system. So you improve a portion. When I say here improving portion, so you are not trying to improve all the execution time. You are trying to improve a fraction of the execution time. Okay, so let us say that F is the fraction of the computation time that we are enhancing. Okay, and let us say that S here is the speed up factor, okay, of the enhancement only. Just we are in, this is the speed up of the enhancement only. Yani, for example, let us say we have an old CPU. Okay, or we have two CPUs, both for the same instruction set architecture. We have an old version and we have a new version. Okay, for simplicity, let us say that the designers, the engineers, they decided that they looked at the old version. They found that the multiplication, the multiplier in the hardware is very slow. So every multiplication is taking, let us say, many cycles to execute. And they decided to improve the multiplier in the hardware. Okay, so they improved the multiplier. They used actually much better circuit, okay, that can do multiplication much faster than the old circuit. Okay, so therefore, they only have improved a portion. So they did not improve the entire CPU. They only improved actually just the multiplier. Okay, for simplicity. I mean. Of course, people now today in real CPUs, they have very fast multipliers. Okay, but in the past, decades ago, multipliers actually used to occupy a lot of area on the chip, and they wanted to reduce the area because technology was not really good at that time. And you need actually large number of transistors to implement a multiplier, and therefore the multiplier actually was slow. It took many cycles to do one multiplication. But today you can do multiplication very, very fast. Okay, and therefore the multiplier is a lot faster. It will use more area, of course. So there is always a trade-off between the area and the speed. So you can increase the area of the multiplier, but then you can actually make it to run faster. Okay, and therefore it's going to take less number of clock cycles to do one multiplication. Right. So suppose that we look here at the old execution time, and then we look at the new execution time. So the old execution time, suppose that the old execution time is just 1. Okay, so that will be the 100% of the total execution time. So for simplicity, okay, let me use here my pen tool. Okay, the old execution time, that's the execution time, the old execution time is equal to 1. Just 1. 1 means what? 100% of the old execution time. That's 1. Okay. I'm going to use a fraction f of the execution time, and we are going to enhance it. For example, suppose that the program is doing a lot of multiplications. It spends most of its time doing multiplication. We noticed that we are doing a lot of multiplication in a given program. And we looked at the fraction of the execution time. So here f is a fraction of the time. So let me say it's time. Okay, it's a fraction of the time. So suppose that 80% of the old execution time, so here f will be 0.8. So the program spends 80% of its time, so we say f equal to 0.8, doing multiplication. And the remaining 1 minus f, that will be the remaining 20%. The program is doing something else, which is not related to multiplication. Okay, maybe addition, maybe loading, storing, branching, okay. So now we see that, okay, so we have here actually the program is spending a lot of time on multiplication. So that's the fraction of the computation time. Suppose that now we would like to have a better CPU. So we decided now we have a new version of the CPU, and I'm going to improve the multiplier in the hardware. So suppose that we improve it by a speed up factor, which is S. So the factor here is S. That's my speed up factor. So we say that if we can improve the multiplier or this fraction, okay, of this fraction of the old execution time, suppose I would like to improve it by a factor of S, then therefore I'm going to reduce, okay, the time here by F over S. So this fraction of old time, we are going to divide it by S because S here is my speed up factor. Clear? Now the remaining 1 minus F, this is the remaining fraction of my old execution time, has not been improved. It's still the same. Okay? Fine.
Yes.
So now we say that is actually, what is Amdahl's law? Amdahl's law actually it's just a speed up. So we divide the old execution time divided by the new execution time. The old execution time is assumed to be 1, and 100% of the old execution. It does not have to be 1 second. No, it can be anything. Okay, so but we just write it as 1. That's 100% of the old execution time. So the old execution time might be T. So we say it is just 1 T. Okay, and the new execution time, it will be F over S. which is shown here, plus the 1 minus f. So that's actually is this. So you can say here, let us say t on top, you write t below, so t divided by t will cancel each other. So we don't really care what's the old execution time. So what is left is 1 divided by 1 minus f. That's the fraction that we did not enhance, plus f over s. That's the fraction that was enhanced by a factor of s. So that's here is the equation for Amdahl's law. Now, this is a very important equation. Now, Amdahl, of course, wrote this equation many decades ago. But still, people actually refer to this Amdahl's law. It's very important. So he used it actually in different ways. Okay, people use it in multi-processors when they talk about multi-cores and so on. They talk about Amdahl's law. So they talk about Amdahl's law everywhere. Right. So let us take a look here at an example on Amdahl's law. Okay. So suppose that we have a program that runs in 100 seconds. Okay, so that's 100 seconds is my old execution time. Okay, with multiplication responsible for 80 seconds of this time. So can you tell me what is f here in this example? What is
80? Isn't
so it's 80%.
0.8.
It's 0.8. Yes. So it's 80 divided by 100, which is 0.8. So my fraction, which is spent by multiplication, is 80% of the execution time. So the old execution time is 100 seconds. That's 100 seconds. And multiplication is responsible for 80 seconds. And suppose that one multiplication takes 100 cycles. Very slow machine, or whatever number of cycles. And I'm just throwing a number here. Okay. Right. So the question is, how much do we have to improve the speed of multiplication if we want the entire program to run 4 times faster? Do you understand the question? We want the program to run 4 times faster. So the question is, how much do we have to improve the speed of multiplication? So what is my unknown here?
S.
Yes, thank you very much. It is S. So what is this S? The speed of factor of multiplication. I don't care actually how many cycles it took, okay, to execute every multiply instruction. What I care about is what is this S, the speed up factor of multiplication, if I want to have the entire program to run 4 times faster. Yani, even though I don't really need to know even Amdahl's law, I can write an equation. So suppose that we improve multiplication by a factor of S. Okay, that's what we need to do. We need to find out what is S. So I can say that 4 times faster is 25 seconds. That's the meaning, right? Because the program took 100 seconds and we want to make the entire program to be 4 times faster. So therefore, you divide 100 seconds by 4, you get 25 seconds. You don't even have to refer to Amdahl's law. You can, of course, okay, put the fraction, and then solve for S. But I'm going to do it differently here because it's very simple. So 25 seconds, that's actually 4 times faster. Now we're going to improve this 80 seconds by a factor of S, because this is the 80 seconds which has been enhanced by a factor of S. So we divide by S, and the question is, what is S? But the remaining 20 seconds are not multiplication. It's something else. And the designers did not do anything about it. They just kept it as is. So they only took the multiplier, the old multiplier, and they throw it away, and they put a new multiplier inside the hardware. Okay. So we are going to improve the 80 seconds by a factor of S, and we are going to keep the 20 seconds unchanged. So the question is, what is S? So we have an equation here, right? The unknown is as S. We can solve it. So what we have to do is that bring the 20 seconds to the other side. So we have 25 minus 20. This would be 5. And then in order to solve for S, we have to divide 80 by 5. This will give me 16. I have to make multiplication 16 times faster to achieve 4 times faster for the overall execution time of the program. You understand this? That's Amdahl's law. Okay? Yani to improve the total execution time, okay, by a factor of 4, to be able to reduce it from 100 seconds to 25 seconds, I have to improve the speed of multiplication. If this is the only thing which is being improved, I have to improve the speed of multiplication by a factor of 16. So I have to make multiplication 16x faster. In other words, let us say each multiplication took 64 cycles in the old CPU. In the new CPU, you divide 64 cycles by 16. Each multiply instruction should take only 4 cycles. Only 4 cycles. So that's actually 16x faster for multiplication. Whether this is possible or not, مش مهم. This is actually what we need to do in order to achieve to improve the overall execution time by a factor of 4. طيب. What if I would like to? So this is the answer to the first part. Improve the speed of multiplication by a factor of s, which is equal to 16 times faster. The second part. How about making the program 5 times faster?
Same procedure, but we'll get a different number.
So replace actually 25 by 20, right? So this will be 5 times faster. So when I solve this equation, what do I get s? Now 20, you bring here the 20 to the other side, it becomes 0. 20 minus 20 is 0. So 80 over s is equal to 20 minus 20. So now if you solve this equation, you get 80 divided by s is equal to 20 minus 20, which is equal to 0, right? S will be equal to what? What is s?
We don't know.
It's 1 or no.
It's 80 divided by 0.
Which is infinity or
yes. So it's impossible to make it 5 times faster. It's impossible. Why? Because you have to reduce the execution time to 20, but you need 20 seconds anyways, okay, for the rest of the program. So therefore, you have to reduce the part which is spent by multiplication from 80 seconds to 0 seconds. And that's not really possible. So you cannot actually you cannot make the program 5 times faster. So no matter what, you cannot really make it 5 times faster. That's actually is Amdahl's law. I have a second example here on Amdahl's law. It says that suppose that floating point square root is responsible for 20% of the execution time of a graphics benchmark, and all the floating point instructions are responsible for 60%. So there is one proposal, is to speed up the floating point square root by a factor of 10. So floating point square root is very slow. And one proposal is to make it 10 times faster. Or there is a second choice, which is making all the floating point instructions 2x faster. So we improve the speed of all the floating point instructions, not just the floating point square root. So which proposal is better? Should we go with the improving the 20%? Should we improve only the floating point square root, okay, which is responsible for the 20% of the execution time, or by a factor of 10, we can make it 10x faster, or should we improve all the floating point instructions by 2x faster, including the floating point square root? So how do we decide? How do we use Amdahl's law to decide that which one should be improved? Okay, so how do you solve this problem? Students? Any response?
Yes.
We can apply the Amdahl's law, right? So we need to quantify this. We need to justify this. It's not just saying that the first one or the second one. We need to say why. And in order to say why, we need to find out the speed up of improvement. Yani, for example, if I would like to improve the floating point square root, what will be the speed up that we can gain by improving the floating point square root. What will be the speed up if I improve the floating point square root by a factor of 10x? Okay, can you tell me what's the speed up?
The 20 will become 12%.
Well, the 20 will become
2%.
Okay, so you divide the 0.2 by the speed up factor, which is 10, yes. And how about the remaining execution time?
Plus 0. I don't know how to go from here, actually.
So, so the remaining 80% of the execution time, does it actually change if we only improve 20% of the execution time?
No, it doesn't.
So we still have the 0.8, right, which is unchanged. If we improve only the floating point square root, we are only improving 20% of the execution time. But this 20% we are going to divide it by 10. Okay, so this is going to reduce the execution time of the floating point square root, but the remaining 80% of the execution time will be unchanged. Okay, yes. So so assume that the initial execution time was 1, the old execution time, before we make any improvement. So we just use the Amdahl's law. We say that the speed up is equal to the old execution time divided by the new execution time. So if we say that, okay, the old execution time is 1, or we can just say t, okay? So here t is normalized to 1. We don't really care what is the execution time. So we just say that, okay, choice number 1 here, improve the floating point square root by a factor of 10. So we say that the speed up is equal to the old execution time divided by the new execution time. So here 1 is the old execution time. In fact, it is just t. But t is going to appear, okay, so in the numerator and the denominator. So we can just take out t. We can just cancel t. So we can normalize here, if you would like, the execution time just to 1. Then the new execution time will be, we take 20%, which is the 0.2, and divide it by 10. But we still have to add it to the 80% of the execution time, which has not changed. It's still the same because we only improve the floating point square root, which is responsible for 20% of the execution time. Now, if you calculate this ratio, you get 1.22. So we have improved it by a factor of 1.22x. Okay, that's if you improve the floating point square root by a factor of 10. Now, what we have to do is that we have to repeat for choice number 2, which is improving all the floating point instructions by a factor of 2. So what will be the speed up if we go with choice number 2? If we improve all the floating point instructions by a factor of 2, what will be now the speed up? Can you tell me what's the equation for the speed up? Yes, go ahead.
Yeah, the old value will be 1.
Exactly. So it's 1 divided by
the square root factor. Oh, I mean 60% responsible.
Yes. So 60%.
It will be multiplied by a factor or divided by a factor of 2.
Yes. So we divide the 60%, which is 0.6. So if you say that the original execution time is 1, then 60% of 1 is just 0.6, right? So we have to divide this 0.6 by 2. And what is missing?
40%.
Which is the 0.6. So therefore, we divide 1 divided. So if I would like to write the equation, okay, of the speed up. So the speed up will be 1 divided by, we have the 40%, which is 0.4. That's not affected by the improvement. Plus, we have the 60%, 0.6 divided by, yes, 0.6 divided by 2, exactly. So this factor has to appear in the denominator. So we are dividing by this factor. So that's the new execution time. So the old execution time is 1. The new execution time is 0.4 plus 0.6 divided by 2. Because we have improved this 60% by a factor of 2. Initially, it was 0.4 plus 0.6. It was just 1. And then after making this improvement, we have divided this 0.6, which is 60% of the execution time, by 2. It's very simple. Amdahl's law is very simple. So you get here the speed up factor, which is 1.43, which is better. Okay, so therefore it is better here to improve all the floating point instructions, okay, by a factor of 2, which are responsible for 60% of the execution time, rather than improving only the floating point square root by a factor of 10x. Okay. So that was an example on the Amdahl's law.